Hello viewers and welcome to a new STM32 tutorial video. I think I need to start this video with a bit of an apology. I have been a bit tardy and it's been almost 2 weeks since my last video. I actually plan to have at least one of these videos a week. But in reality, I have not been that tardy. I had a tentative plan. As you know, I'm not really planning these in advance, so it's a bit improvised how I moved on. And my plan was to make the next video about I2C or I2C, but that turned out to be a little bit more complicated. Not that I couldn't do it, but it was hard for me to make a video that was actually a tutorial, an easy tutorial video, and I'm still working on that, and I will get back to it. But for now, I needed a couple of topics that were simpler, so they fitted um, a video format like this better. And while going through my junk boxes for various I2C sensors, I came across these little boards that I made a long time ago. In fact, I think it was the first board I ever made from DLC PCB, but well, I'll get back to that. And this came about, well, it's basically a board that contains a so-called rotary encoder. And this came about because it came about some really cheap rotary encoders. I think it was this one or something like that. So 5 pieces for $1.50. And these rotary encoders, they basically count 20 pulses on a complete circle, and it's got a button as well. So if we look at the pins, these 2 pins are the buttons. So if you press this, this will short, and on the other side you have a common pin and 2 pulse pins, and those pins will toggle on off as you rotate this device. One of the problems with these devices is that it is a mechanical device. Inside there's a little copper thing that slides against another copper thing, and when it connects and disconnects, there is some noise generated, some small pulses that are not supposed to be there. Those pulses is called bouncing. And the idea about my board here was that you can filter out these bounces by adding a low pass filter, an RC filter. So I basically have a capacitor and a resistor, and that cleans out that noise. So if we look at the schematic of my board here, the idea is that it is pulled up when these are both disconnected. It's pulled up to VCC, so there will be 3.3 volt coming out here. Once this go low, it will connect these to this, and it will go to ground, but it will discharge the capacitor through the resistor, so it won't go low immediately. It will take a few microseconds for it to go low. We could calculate that it's 10k and 10 nanofarad, so it's quite easy to calculate the cutoff frequency, how long it takes for it to dive. But this is the values I came up with that are pretty optimal, and you can see I'm doing the same with the button. So you have A and B, and the button are all debounced through this. Now, why are there 2? I hear you ask it, because one should be enough to count these pulses of a rotary. Well, the idea is you can determine the direction of the rotation, and it does that by having the 2 output signals 90 degrees out of phase with each other. So you can see the A pin here will go like that, and if you keep rotating in the same direction, the B pin will do like this, go like this. And that is simply how all these rotary encoders work. You can see you can also get really high precision models here. I think this one goes up to, you can see you can have 2500 pulses per rotation. Of course, and connect that mechanically up to something where you want to know the position of this, the rotation. Sorry. Now, how do you read these rotary encoders in STM32? And the reason why I come up with this video is that, believe it or not, you can actually use a timer for this purpose. I have made earlier videos where I'm using a timer to generate an interrupt every second. I have done some where I use pulse width modulation to play around with a LED or 4 LEDs. Actually, I'm doing in one of these PVM videos. In this case, I want to do a timer rotary encoder video, and as usual, I have started my basic project here by enabling the necessary clock frequency, external clock, setting up the board, and I have created a redirect of print, so it prints out on my serial port, and I have started my basic project. So let's run that, and as usual, it will just print out starting and then a tick every second and counting the loops that it goes through. Now let's look at the timer, and if we go into the timer configuration, and I'm using timer 3 for this, I think you can use 2 or 3 others. So the idea is that rather than giving it a clock source, you use the rotary encoder as a clock source. And you do that by combining 2 channels. So if we go down here, you can see we can actually enable this timer in encoder mode. And when you do that, it will enable 2 timer channels and keep track of 2 timer channels at the same time. There's actually nothing to necessarily be set up in here. It will just basically keep track on the counter depending on which way it is rotating, but we will enable the interrupts. Now we also have the button pin, so let's enable this one as an interrupt, and let's give that a user label and call it button, and then we need to go up in our interrupt settings and we need to enable that external line interrupt, and we need to where is that? The GPIO. We say that, so we will just detect on a falling edge transaction. Doesn't really matter which one you're using. So this is the basic STM32 Cube IDE configuration to do this. So let's try to generate this code. In order to use this feature, all we need to do really is to enable our timer. So after we print starting, let's fire up the timer, and we will do that in TIM encoder start IT. That means it'll generate an interrupt every time a transition happens. But for now, let's just print a little more statement here. So print rotation, and that would also be there, and we can print SIM3, that's our timer, and it is our counter. So let's try to print this out, run this. I have already hooked up that rotary encoder to my board. And you will see it comes out with a rotation of 0. But if I turn the knob on the rotation encoder, you'll see that it changes the values. So that is all that is needed to detect one of these rotary encoders. Now we can improve this a little bit. Of course, we can basically, let's look at the button. No, let's say rather than printing it out here, we would like to print it out every time it changes. So we will create a couple of variables to keep track of this, whereas our private variables are here. So we will have we'll do that as an integer. In a 16-bit integer, we call R, and we set it to 0 initially, but we will also have a flag R change, which we also set to 0 for now. Now we can, in our we can handle the callback, the interrupt that happens, and we can do that down here. We can add a timer IC input capture callback, so it will basically store our count in R, and then our change, we set that to 1. So now down in our loop, well, we can still print it out here, it doesn't really matter, but we can do if R change, we print the value out, and we print out R, and then we have to remember to say R change, set that back to 0. So now if we run this, it actually prints out every time. You'll see that we actually get 2. And the reason why we get 2 is that there are 2 pulses. Well, that actually, there's a little bug here. This should actually be a D, isn't it? Percent D, because it's only a 16-bit value. That should also enable it to be negative, if I'm not mistaken. That doesn't work. Oh, yeah, comes out with negative values. We could also look at the callback from make the button have a function, and we can do that with doing an external interrupt callback. So up here we add this. So basically when we press the button pin and the counter is different than 0, basically what we will do is we'll set it to 0, so we can use the button press as a reset back to 0. Let's try to see if that works. Something failed there. Button pin, didn't I give it a name? Yeah, but I wrote it wrong. So let's call it BTN button, and generate our code. And now it should build and flash. So first, let's try to press the button without actually rotating. Nothing happens. Let's rotate. And let's press, oh, it went back to 0. Let's try to press the button, and it goes back to 0. So that is all that is necessary to actually interpret a rotary encoder. using a timer and two timer channels in a timer. It is surprisingly simple, and it's just one of the many features of the timers in an STM32. I want to point out one little detail before we close this video, and I wrote this article in the STM32 World article wiki a while back, and if you read the article, I will explain that phase shift more in more details, and this is basically what I've done in this video. But one thing I realized when I played around with this timer was that why not actually handle this as an interrupt-driven state machine? So rather than using a timer on it, simply handle these interrupt, because what happens is, if we look at this drawing, what we're looking at is actually changes, state changes. So this one, it's go from high to low to low, and depending on the direction, these changes happens in a certain order. So as I described here, for the phase transition will be 3 2, 2 to 0, 0 to 1, and 1 to 3. If it rotates the other way, it'll go from 3 to 1, 1 to 0, 0 to 2, 2 to 3. And we can handle that as a simple state machine down here. The reason why the timer has one value that this one does not have. Remember, in the beginning of the video I mentioned the debouncing. These rotary encoders are not very good quality, and they bounce quite a lot on that shift. The timer actually have some filtering built into the code, and you can actually adjust that down here, input filter, that helps debounce this. So if you don't have all this circuitry with your rotary encoder, it is probably best to use the timer. But in my case, where I have this filter down here, actually the state machine works perfectly okay. So that is pretty much all I intended to do in this video. I will probably make another short video. I have a few ideas before I end up doing my I2C or I2C. Just make it absolutely clear, I usually call it I2C, but I think most common is I2C. Doesn't matter, I'll get back to that in a later video, but meanwhile I'll post a couple of short videos just to make sure that the channel is still active. That's about it. As usual, please like and subscribe if you survived this far. And I read all the comments, so please comment below if you have any comment, and have a wonderful rest of the day.